Okay, so hello everybody and good morning, and it's great to be back meeting you all again. I'm sorry I can't be there in person, but good to meet you, and thanks Terence for setting up this webinar, which is an introduction to insertion loss. So we'll go through a number of slides and look at what influences insertion loss, how it contrasts with impedance, and we'll look at the modeling tools available, and we'll look at measurements and how you figure out modeling and measurement. So I think you'll all be familiar that more and more of our customers are asking for insertion loss requirements, especially for ultra-high speed digital communications. And this presentation is really to show you how modeling and measurement work together to ensure reliable prediction of multi-gigahertz transmission line performance. So when we're signaling at very high speeds, normally at lower speeds, all of the signal that you put into the transmission line arrives at the other end, but with very high speeds, when you get into multi-gigahertz, then some of the signal is lost as it travels down the line. So you can think of it as a bit like a sound, where at the start of the transmission line, the sound strength is very strong, but as you move down the line, if you imagine yourself traveling down the line, the sound gradually gets quieter, quieter and quieter until there's no signal left at all at the far end. And the reason that signal gets less and less for two reasons. And the two reasons are copper loss and dielectric loss. And we'll take a bit of a look at both of those. So if we look at copper losses first, the first thing is the DC resistance of the trace. And normally if you're calculating the DC resistance of the trace, you'll put in the resistivity of electrode deposited copper and then work out what the trace resistance is per length of the trace. That's usually fairly low, but some of the high frequency effects magnify that DC resistance. And in the next slides, we'll look at how that DC resistance is further affected because of the way the signal travels at high speeds. So even if your DC resistance is quite low, what you find is that higher frequencies, the current is pushed out closer to the surface of the copper, and that reduces the cross-sectional area you've got to travel through for the current to travel through, so the effective resistance increases. So the higher the frequency goes, the more the current is traveling on the surface in an ever smaller amount of copper. So on the next slide coming up, I'll gradually reveal what happens to the signal as the frequency increases. So you'll see a blank screen, and then gradually the skin effect is displayed on this next slide. So watching from the top, at 10 megahertz, you can see the current flows through most of the trace. 100 megahertz, it's almost all carried on a few microns on the outer. And then the skin depth is about 1 micron at a gigahertz. So you can see as the frequency increases, there's less and less and less copper for the current to travel through. So that's a picture of how the skin depth develops. On the next slide, we can see graphically we're increasing the frequency, and you can see as the frequency increases, the depth in the copper. Let's just highlight this. So at 100 hertz, you've got 6 microns, then you've got to kilohertz, 10 kilohertz, so on. And approximately, it's around about a micron at a gigahertz. So as the frequency increases, the depth of the current flowing reduces and reduces, and equally we've got a curve showing the resistance as it increases as the frequency goes up here. These are graphs you can easily produce using the SI9000 field solver. This was also produced as part of Eric Bogatin's book. So now we've described that the current's starting to flow on the surface of the trace, it's important to consider the roughness as well. So we'll look at how roughness is going to affect the losses too. Here's a very magnified microsection just to show the roughness. And of course, you can get different degrees of roughness with copper, but also the roughness will change with the treatment of the material. But this is just to show you where I've shown the pictures of where the current's flowing. It's flowing on the outside edge of the trace, and when you look at the base of those two signal traces, that's where all the roughness is. So that needs to be considered in the modeling when you're modeling roughness and losses due to roughness. So the the loss from copper losses, the resistive losses, that's the power loss. It's turned into heat basically as current drives down the trace and returns through the plane. Then current traveling through there as the signal switches high and low turns into heat and gets lost, so it's no longer used to convey the signal. So that's where part of the losses occur. The other part comes from losses in the dielectric material itself. So what's happening is you charge and discharge the substrate, the energy is consumed rotating the molecules in the varying electric field. There are many different substrates available, so if you use conventional FR4, then the dielectric loss is quite high, you'll lose a lot of energy and the loss will be quite high, and you can get a whole range of different materials which have got lower and lower loss, and typically they cost more money, so you have to trade off the low loss material versus the cost of the substrate. And by using modeling tools, you can trade off to figure out whether you're best using smooth copper or whether you should use low loss materials or whether you need to combine both of those. But sometimes it's very useful to visualize or actually feel effects of these in real life to see what's happening. So with dielectric loss, you can do an experiment with a piece of unclad FR4 in my microwave oven. And if you put an ordinary FR4 sample, not copper clad, you'll find that the FR4 warms up when you heat it in a microwave oven. And that's dielectric losses actually heating up the fiberglass substrate of the PCB material. So the reason for modeling is that when you model the insertion loss, it lets you break down the losses and look at the key influences of loss, and that helps you to calculate which parameters you need to adjust to get the loss within specification. So the characteristics you need to control for loss differ from those for impedance. They're both important, but the physics that affects loss is fundamentally different from that affects impedance. It's important to get the impedance correct because that helps you get the maximum energy into the transmission line, but once it's in there, different parameters affect the amount of signal that get lost from those that affect the impedance of the line. So they're both important, but you need to control different parameters for loss for those you control for impedance. If we look at impedance, and I know there's a question coming from Jason Lynn, so we'll go back and cover that later. So that's good. Thanks for that question. We'll pick that up and answer that on the number of boards and the hero method. So thank you for asking that question. We'll pick up the questions if we've got time at the end, and if we don't have time, then we'll follow them up by email or with application notes. So to just go back and recap to review on impedance. So what affects the impedance? Well, the width of the trace, the wider the trace, the lower impedance, the height, the lower the height, the lower the impedance, the thicker the coating, the lower the impedance. So the substrate height, the trace width, and then the dielectric constant has a slightly lower effect. It's a square root effect, 1/, square root effect, but the dielectric constant is important for characterizing impedance. So trace width, height over the plane, and the dielectric constant of the material, those are the key drivers for impedance. So next we'll look at the key factors for controlling loss. So the first thing you need to consider is the loss tangent, and that's the loss tangent. The higher the loss tangent, the more energy will be consumed by heat in the substrate. So when we had the microwave oven demonstration earlier in the presentation, a high loss tangent will cause more heat to be lost when this trace is charged and discharged. Heat gets dissipated in the substrate. Then at lower frequencies, for the copper losses, at the lower frequencies, the current's traveling in the whole of the copper trace here. But as the frequency increases, then gradually the current travels out to the surface. So you've got an increasing loss because the copper is carrying the current only the outer surface of the trace that I'm outlining with the pointer here. Just the very outline carries the current. And then above that frequency, you start to increase that more. And then the roughness takes into account, and I've superimposed the roughness here so you can see the roughness on this trace, and with the current flowing here and in the opposing face here. Okay, so here's the return path, again a rough surface, so you've got copper flowing on this roughened surface, which further increases the loss. So if you go back and think of the image that you've just been looking at, you can imagine how careful stack up can reduce losses. So I'm going to go back to that slide again, and think about this. You've got the roughness here and here. Typically, if this is a core material, that's for a controlled impedance, you'd normally fabricate the critical traces across the core, and you've got a rough side here and here. But if your copper had the rough faces on the inside, you could stack across the other way. If you had a foil like this, where you have this face and this face carrying the signal, then with the same copper foils, just having the signal on the other surface, by flipping the stack up round, you could reduce your losses, and you can model how that works by using the SI 9000. So modeling, we'll look at modeling. There's a phrase that we always use at Polar seminars that says, and it's not our phrase, it's George E.P. Box, who was an eminent statistician a long time ago. He said, all models are wrong, but some are useful. So that's true of all modeling software. The models are as good as the data you put in, and they're very good to give you an idea of what you're looking at and what parameters you need to adjust. So that's a useful thing to bear in mind when you're looking at all modeling software. So models are only as good as the data you input. So the better data you put in, the better modeling you'll get of the loss. So here's a list of things that you need to model loss. The loss is proportional to the length of the line. So you need to know the length of the trace that you're predicting the loss in. You'll need to know the loss tangent of the materials, and that includes both the laminate and the solder mask. You also need to be aware that sometimes solder mask, if it's not fully cured, will absorb water, and that will affect the loss measurements and the loss modeling. So solder mask needs to be well cured to ensure it doesn't absorb any water. You'll need to know the conductivity, and if you're putting the conductivity into a field solver, you need to use the conductivity for electrodeposited foil as opposed to rolled and annealed foil. ED foil has got a slightly lower conductivity than rolled foil. And you'll also need to know the copper roughness, but not off the data sheet. You need to know the roughness of the copper after it's been processed for adhesion promoters or any pre-treatment that you're applying to the copper in the production process. So whilst you can get very smooth foils, if they're on layers with drill ends on them and they're going to be plated up, you need to know the after plating or after the pre-treatment for adhesion promotion. So all of those factors are important in terms of data you're going to feed into the field solver for modeling loss. I've put up a coated microstrip here, made it 50 ohms, and so this is the, and it's got a dielectric constant of 4.2. We now move into the frequency dependent tab, and here you can see again the same structure, same dimensions, but here we can actually calculate the loss. So we're looking at the losses in dB per line length. So I can look at the length of line. In this case, I've got 1,000 mils or 1 inch, that is. I can look at per inch or per meter. In addition to the dimensions for impedance, we've now fed in the trace conductivity, the loss tangent, and the minimum and maximum frequency, and the number of steps we're going to calculate. And then in the graph, we'll display the conductor loss, the dielectric loss, the total attenuation without roughness, and then the conductor loss with roughness and the attenuation with roughness. So we can break down all of the insertion loss into its component parts. So we discussed those in the first part of the presentation. I'll calculate now field solver runs, and here you can see the red line, which is the conductor loss, and then the green, which is the dielectric loss, and so on. In fact, if I take this down to a lower frequency, let's go down to 100 megahertz. Let's go down to 1 gigahertz. Okay, so you can see that at very low frequencies here, the dielectric loss is quite low and the conductor loss is higher. And then as the frequency increases, the dielectric loss overtakes it and becomes the main factor of loss. But here what we're doing is breaking down the total loss. And in this case, in this 1 inch, we've got 0.16 dBs per line length. I made this a 10-inch long line. Calculate. Okay, so now we're up at 1.6 dBs on a 10-inch line. And if I push the frequency up to, say, 20 gigahertz, now you can see as the frequency goes up, the dielectric loss continues to rise and rise and rise, and the copper loss is less so. So the red is the copper loss without roughness, and with roughness is here in yellow. And then we've got the dielectric loss with just straight copper, and then copper with copper roughness. So that lets you pick apart and analyze each component of insertion loss to see for your particular design which is the biggest influencer for the loss that you've measured. So with the SI9000, apart from modeling the basic geometry, you've got different ways of modeling the way the substrate behaves. So for simple modeling, where you'll just want some basic numbers, constant dielectric constant, constant loss tangent. But if you want to more precisely model how the dielectric constant will vary as the loss tangent varies, you can click here, and this allows the field solver to predict how the dielectric constant will vary with loss tangent. So this sweeps loss tangent over frequency and sweeps dielectric constant over frequency, and basically with the lower loss substrate, the less the dielectric constant will vary. But this does the calculation for you, so we needn't talk too much about that, other than to say we can model the substrate data performance over frequency by entering the loss tangent, and the amount of loss tangent will predict how much the dielectric constant will vary over frequency. You can do that by calculation, or if from the data sheets you've got the data for the materials you're using, you can add in a table of frequency, dielectric constant, and loss tangent. So that's two different ways you can model the way the dielectric constant and loss tangent vary with frequency. For roughness, we can model smooth. I'll run this again. So here we've got the modeling without any roughness. Hammerstad is a fairly old way of modeling roughness, but it works up to 7 or 8 gigahertz quite well. Groisy slightly better, and then Hure, probably the best way of modeling roughness, but Hure requires input of data from a scanning electron microscope for the model of roughness. So we've helped you a bit there. We've actually added in a technique called cannonball Hure, and cannonball Hure actually calculates the ball radius and the ball count for you. So you simply put in the RZ mat and RZ drum in here, and it will calculate for you the parameters for Hure. So that makes the Hure method much easier to use without the need to put in data from a scanning electron microscope directly. Just one last thing, I've gone up to 40 gigahertz here, and you can see that at 40 gigahertz, almost all of the loss is in the dielectric. So the dielectric becomes the predominant loss at the much higher frequencies. Measurement is, all we can get from measurement is the total loss at frequency. So you need the modeling tools to extract the information from the measurement. So we'll move on to the video which shows you the introduction to the delta L4 method. And let's skip through these. You'll need a coupon. Yeah, so with measurement, here's a measurement out to 40 gigahertz, but there's just one line. It's the total attenuation, and that's the combination of the copper, the dielectric, and the roughness losses. So this is a 5-minute introduction, so that will take us just to the wrap up of measuring insertion loss using the delta L4 method with the Polar Atlas software and an Anritsu Shockline Series 43 GHz network analyzer. Welcome to this brief introduction to PCB insertion loss measurement with Atlas for VNA. In order to extend our testing capability above 20 GHz, Polar's partnered with Anritsu to extend testing for insertion loss up to 43.5 GHz. We do this by connecting with an Anritsu 43 gig VNA. The method being used for testing insertion loss is the Delta L4 method. It can be used in production or material qualification, and I'll show you a few screenshots of the Delta L4 test and how to set it up, and then follow up by showing that it's always important that you cross-check by microsectioning and feeding your results back into a field solver when you're initially setting up insertion loss testing. Here's the familiar Atlas test environment with the list of test vehicles on the test coupon on the left-hand side, the insertion loss curve on the right-hand side of the screen, and the data log area at the bottom of the screen. The data has been processed from the S parameters from the VNA using eigenvalue Delta L4 method, and a line fit has been made to the insertion loss curve, and you can see we've got a good line fit here extending right up to 40 GHz. Here's another example. Again, this is a different trace on the same test coupon, and you can see again the line fitted right from low frequency all the way up to 40 GHz, and there's a cutoff frequency which I'll show you in more detail a little bit later, showing you the maximum frequency where we're confident of credible results. If you look at the lower frequency, you can see the slight curve as the skin effect fully develops in the copper part of the trace. The Delta L processing with eigenvalue processing allows the maths within Atlas to calculate the certainty of whether a particular point should lie on the line fit or not. And in this particular display, I've brought up three graphs: the processed line fit and the data processed by eigenvalues, and then the uncertainty for each point. So this shows that at the lower frequency there's a high uncertainty, and then as you get into a gigahertz or so, the certainty of the data points is very good, and then at this point at 30 GHz there's a very high level of uncertainty, and these two numbers are used to process the maximum frequency at which we can trust the results. So you get a cutoff frequency, and I'll show you that on the next slide. So I've just highlighted and popped out the results in the right hand side of the screen, and you can see here that there's a cutoff frequency. Again, this has been calculated automatically, and it says the maximum frequency that this result is credible at is 31.4 GHz. But we've got a good solid result and a good solid line fit up to that point. This is another test which shows you again the processed and fitted data, the uncertainty, and the raw S21 data that we're processing to calculate the final results. The Delta L4 method takes in all four S parameters for the line. The test setup for making an insertion loss test with Atlas is very straightforward. You simply enter a description for the test you're making, the layer number if that's of use to you. For materials qualification or for critical tests, you can use 3-line Delta L, but normally in production you'd uncheck that and use 2-line Delta L. You specify the length of the short line for testing and the long line, the units in inches or millimeters, and the display loss per inch. And then the test limits, frequency cutoff, and the test limit for the frequency and the max dB loss at each individual frequency you need to sample in your test program. So it's very straightforward. It should be very familiar if you're an existing Atlas user. And here's another example test that I've displayed for you. Once you've got your test results, it's quite a good idea if you're working on a new project or a critical project that you microsection the board, the test vehicle, and take a microsection and measure it and pass the results into Field Solver. So here's a microsection. You can take the data off that microsection, including any surface roughness data you can get from the microsection, and you take that information and then feed that into a field solver such as SR9000, and there you can work out what you would predict the results to be based on the section data, the roughness data, and you can analyze from this data the biggest contributor to loss, whether it's copper loss, roughness losses, or dielectric losses. The field solver lets you do this analysis in great detail. Thanks for watching this brief introduction to Atlas for Anritsu VNA and the use of Delta-L for insertion loss testing on higher frequency PCBs. Okay, so that was the introduction to testing with Delta-L. We covered the modeling, measurement, and microsectioning. Terence, is there anything you'd like to add?
I think you did very well, cover a lot of stuff.
We can run up the Atlas software and show you. See this here. So with Delta-L testing, it's very straightforward. I mean, it's really giving you a much better line fit than previous methods for insertion loss testing. So what it does is it helps de-embed the effects of any vias or uncertainties within the trace. And so I'll just share the application. So what you can see here is as the frequency goes up, you'll sometimes get effects which are dips down here, or you'll get variations in the measurement as the frequency goes up and above and below the actual line for the insertion loss. Delta-L looks at the points either side of the point that's being analyzed to see if they're in the same sort of area, and uses that to enter the data into the line fit. So if there's a dip that goes wholly negative here, or a dip that just went totally positive, so if you've got a dip here from a via stub, traditional line fits would tend to pull the line down like this, whereas with Delta-L, it's intelligent enough to say, well, actually, this dip is only going one way. I'm going to ignore this and actually put the points from here and here into the line fit. So it helps de-embed the effects of the via. It can't completely take them out, but it does a much better job of de-embedding than earlier methods of de-embedding. And this is the graph here. We can see it's uncertain because of this via, but it's not actually affected the line fit. So and on here you can also see the S21, which is the raw data from the S parameters. And if you're interested, you can actually look at the whole source S parameters here on the so you can look at the S11 for the input reflection coefficient, S21, S22. The full suite of S parameters are available on here for diagnostic purposes. So back to the main result. So normally you'll be looking at this, but here's one test, here's another different test. Again, you can see here's one with a large positive spike, but again, that large positive spike doesn't pull away the line fit. So that's the key takeaway for Delta-L, that if there are large deviations from the overall line fit, Delta-L is very good at ignoring the points that are not relevant and emphasizing the points that are relevant. Okay, so yeah, briefly in summary, we presented the mechanisms behind impedance and insertion loss, how the key factors that influence impedance are quite different from those that influence insertion loss, how you can model insertion loss, and then how you can microsection to look at the physical parameters you need to put into the field solver, and then looking at the measurement, how to understand that all you can see from measurement is total loss. So the only way you can extract total loss and turn that back into roughness, copper loss, dielectric loss is by mixing the modeling and the measurement, by putting the measurement numbers back into the field solver and comparing and contrasting the results. Once you've figured the model, the measured, and the mechanical measurements, then you can have a very good understanding of what's driving the levels of insertion loss in your PCB. And certainly the Delta-L version 4 makes it easier to push the measurements up to higher frequencies, but it's still important that you've got a good design of test coupons. But the complete package makes it very easy to analyze insertion loss. So thanks very much for attending, and I look forward to meeting you on the next seminar. Hopefully next time travel will be back on, we'll all have injections and we'll be back visiting with COVID-free in China. I look forward to getting on an airplane and meeting you all again in person.